Assalamualaikum and hello everyone. So we're going to continue with the second subtopic, which is calorimeter. Okay, so this subtopic has lots of calculations and a few new terms that you need to know, which are heat capacity with the big letter C, specific heat capacity, small c, and then calculations where you have to calculate the heat change or Q reaction in constant volume calorimeter, or known as bomb calorimeter. Calculate heat change Q reaction in constant pressure calorimeter or coffee cup calorimeter, or simple calorimeter or solution calorimeter. Okay, so how can we measure heat changes? Basically, we're going to use calorimetry. It is the measurement of heat changes of a reaction, and the device that we will use is called a calorimeter. So it will measure the heat released or heat absorbed by a physical or chemical process. Okay, so there are two types of calorimeter that we will learn, which are bomb and coffee cup calorimeter. So the calorimeter that we will use in our labs will be the simple calorimeter. Okay, so the measurement of heat changes will depend on an understanding of heat capacity, okay, big C, and specific heat capacity, which is small c. So let's see what are these C's. Okay, so to understand heat change, we need to know that the quantity of heat absorbed by an object, or denoted by Q, okay, heat absorbed by an object is proportional to its temperature change, delta T. Okay, the more heat that is absorbed, alright, the larger the temperature change. Alright, so if we put an equal sign, we will get our C, big C, which is heat capacity of a substance, as a constant. Alright, so C is the heat capacity of a substance. That means how much heat a substance is able to contain to increase in temperature. So delta T is basically just T final minus T initial. About heat capacity of a substance is that every object has its own capacity of absorbing heat. So when different substances are heated with the same amount of energy, okay, basically same amount of heat, they will not give the same temperature change. Okay, the delta T will not particularly be the same for different substances. So different substances can have different heat capacity. More about heat capacity, which is the capital letter C of a substance. It is of a substance, okay? It means amount of heat required to raise temperature of a given quantity of substance by 1 Kelvin or 1 degree Celsius. So in heat capacity of a substance, we are going to emphasize on a given quantity of substance. Okay, so how much heat you need to raise the temperature of any given quantity of your substance. Okay, it's not specific. So this is the symbol for heat capacity. This is your heat change. This will be your delta T, which is temperature final minus temperature initial. And the unit for heat capacity will be joule per Kelvin, because energy is in joule and temperature is obviously in Kelvin or degree Celsius. Okay, heat will equal to capital C delta T, C theta. Okay, alright. So next term you need to know is specific heat capacity. This is the small c of a substance. So the difference is that, okay, let's look at the definition. It is the amount of heat required to raise temperature of 1 gram of substance by 1 Kelvin or 1 degree Celsius. So how much heat is required to increase the temperature of 1 gram of a substance by 1 Kelvin or 1 degree Celsius. So for specific heat capacity, it is specific to 1 gram, unlike the capital letter C. Okay, it already take account of the mass, okay, in the big letter C, but specific capacity does not. Okay, so the formula for specific heat capacity of a substance is heat change over mass of substance and the difference in temperature, okay, delta T or theta. Okay, since heat capacity is this, alright, so it already takes account of the mass times with the specific capacity. Therefore, heat change will be equal to Q equals to mc delta T, or Q equals to mc theta if in physics, right? Okay, so basically you can interchange between the formula before and this one. Okay, the unit will be in joule per gram per Kelvin or joule per gram per degree Celsius. Okay, so this per gram refers to specific to 1 gram of substance. Okay, how much heat is required. Let's say if we have the substance which is water. Okay, here we have our water. So for water, the specific heat capacity of water is 4.18 joule per gram per Kelvin. So this means that we need 4.18 joule of heat, okay, heat to increase the temperature of 1 gram of water by 1 Kelvin or 1 degree Celsius. Okay, so that is what is meant by specific heat capacity. When you read this is what it means. Okay, alright, next we have the enthalpy change. It is measured by using calorimeter. So there are 2 types of calorimeter that we will learn. So each calorimeter, it consists of system of different components. Okay, they can be called constant volume calorimeter for bomb calorimeter and constant pressure calorimeter for simple calorimeter. And what it means by system of different components, the Q reaction will be equal to different components in the system. Okay, for example 1, it asks to calculate the specific heat capacity, the small c, of copper, given that 204.75 joules of energy, this is your Q, raises the temperature of 15 grams, this is your mass, of copper from 25 degrees Celsius, the initial, to 60 degrees Celsius, the final. So right here, we want to find the specific capacity. So using the formula Q equals to mc delta T, we can actually rearrange the formula to find specific heat capacity. So Q over m delta T, right? Okay, so just plug in your values. Okay, this one is in joule, and then over your mass is in grams, multiplied by your change in temperature, so 60 minus 25 degrees Celsius, and then you should get this answer. Okay, so make sure your units are correct. Okay, tally with the units that you used, the SI units you use in the formula. So do this by yourself, and here we have the formulas, okay, for heat change. These 2 formulas you need to remember, and make sure you don't confuse between the small c and the large c. Okay, so the small c is your specific heat capacity, so you will have mass in front it. Okay, mc delta T. For heat capacity of the substance, you do not have any mass because it is already equal to mc. Okay, it already take account of your mass of the substance. Okay, so heat is a form of energy transferred between a system and its surrounding as a result of temperature difference. So heat passes from a hot body to the colder body, the heat release is equal to the heat absorbed. Okay, so right here, this is our focus for this slide. If you learn physics, you know of conservation of energy, right? So your energy, it will not be destroyed, but it will be transferred, okay, from one object to another. So generally, heat released plus heat absorbed is equal to 0. Okay, this is like the balance of the universe. So therefore, the heat absorbed is equal to negative heat released. Okay, so basically it's just maths lah juga bawa sebelah, right? And now we're going to look at the first type of calorimeter, which is simple calorimeter or coffee cup calorimeter. It's called coffee cup calorimeter because we have a styrofoam here, the outer styrofoam cup, which acts as insulator. Okay, insulator maksudnya dia tak absorb heat and make sure there is no heat loss to the surroundings. Your surroundings is out here, okay, so there's no heat loss. Tak ada, because this styrofoam cup is an insulator. So it is suitable for measuring enthalpy change, okay, delta H, for reactions that take place in aqueous solution. Okay, this is important. So when you get a coffee cup calorimeter, it means that your reaction will be non-combustion reactions like neutralization, solution, or hydration. Okay, yang guna solution saja. Okay, heat released by the reaction, okay, heat reaction is absorbed by the solution and the calorimeter. So basically what will happen here is that, okay, let's say if we have neutralization reaction, you have your base in here and then you add your acid, okay, or either way. And when that happens, okay, you close your coffee cup and you will observe the initial temperature before that, and then when your reaction happens, okay, while your reaction happens, you will need to stir it to make sure that your solution is mixed well in the styrofoam cup, and then you're going to look at the final temperature pula. The reaction that happens in here, okay, your Q reaction, the heat of the reaction will be absorbed by your solution in here, okay, your solution, and the calorimeter here, okay, we are assuming that there is no heat loss to the surrounding, okay, it is absorbed by the solution and calorimeter. That's for simple calorimeter, okay, so it's important for you to know the heat release, it is absorbed by what, okay, in your system. Okay, so this is important. Alright, this is what I was talking about. The heat of your system is equal to your solution, calorimeter, and reaction. Since no heat enters or leaves the system, that means that the heat of your system is equal to 0. We can find the heat change for your reaction. So in order to find heat change, then we will rearrange our equation here to get this, okay. So here we have heat change, okay. Notice that I say heat change, not heat release, okay, heat change. So it will be equal to negative this, okay. So what is this? This is the heat of your solution, heat absorbed by your solution, heat absorbed by your calorimeter, okay. And this one will be equal to mass of solution times specific heat capacity of your solution times delta T mc theta. Okay, for Qcal will be heat capacity of your calorimeter and delta T. Okay, so this is important for simple calorimeter. Alright, so please note that the heat change of your reaction will be equal to joule or kilojoule, okay, because it is just heat, not specific to 1 mole. But if you have enthalpy of your reaction, let's say enthalpy of neutralization, enthalpy of solution, okay, then you will need to find your delta H of reaction. So this one will be specific to 1 mole. So your unit will be in joule per mole or kilojoule per mole. Okay. To find the enthalpy of your reaction, you will need to use this formula, which is heat change of reaction over mole of ... So let's say for neutralization, okay, ni penting daripada the last subtopic. Okay, you need to know the definition. 1 mole refers to who? Okay, for neutralization, 1 mole will refer to the mole of water. So you're going to put, let's say kalau ini neutralization, then this is the heat change for neutralization reaction. The mole will be the mole of water formed during the reaction. Okay. So ingatlah, this is important, okay. Dia minta heat change or heat released or enthalpy. Okay. Heat of reaction. Okay. Keep in mind that for aqueous solution, the density and specific heat capacity are usually assumed to be the same as for water. Okay. So kalau dia tak bagi tahu, maksudnya you can just assume je that solution tu dia punya density is 1 gram per milliliter and the specific heat capacity will be the same as water juga, 4.184 joule per gram per degree Celsius. So this one you can refer to your list of constants kat depan. This one will be there. Okay. And another thing to note is that some books, they ignore the heat loss to the calorimeter itself. Let's say macam styrofoam or thermometer. Okay. So therefore, instead of your Q reaction being this way, okay, yang ada Q cal ni, okay, they will not mention Q cal, they cancel out. They ignore the heat loss to the calorimeter. So you will end up with this formula. Okay, so we have example 3. So there are 2 different solutions that were reacted in a constant pressure calorimeter. Simple calorimeter, okay? So it has this heat capacity of 335 joule per degree Celsius. And the initial temperatures of both solutions are the same, 24 degrees Celsius. Okay, so ini the initial. And the final temperature is 27 degrees Celsius. Calculate the heat released by the reaction. Bukan heat change tapi negative Q reaction. Okay. Kalau Q reaction saja, maksudnya this is heat change. Kalau heat release, it is like this. Okay. Dia dah take account of negative tu. Dia bawa sini. Heat release. Berapa banyak heat released. If the total volume of mixed solution is 200 ml, so this is your volume of solution lah. Okay. So, since we know that this is simple calorimeter, okay, sebab dia kata constant pressure calorimeter, therefore, you will need to automatically think of the heat of the system, okay. So, heat of the system consists of solution, calorimeter and reaction will equal to 0 because there is no heat escaping to your surrounding. Okay. Assume that the densities and the specific heats of the solutions are the same for water. So here we have density and the small c specific heat capacity of your solution. To answer this question, first of all, you need to know what calorimeter this is so that you can identify which formula to use. Okay. So constant pressure maksudnya it is the simple calorimeter. So therefore we are going to think of this equation and automatically get this formula. The heat released by your reaction is absorbed by your solution and your calorimeter. Okay. So kalau solution, you will use MC theta. Okay, MC delta T. Your calorimeter, you will use C cal delta T. Okay. Ingat And you have negative here because this will be heat change. Okay, this will be heat change. Alright, so this one is heat change. Okay, note that. Okay, next. Okay, you have this, you have this, you have this, you have this. But where do you get the mass of solution? The hint is you will get it from the density of solution. Okay, since density is equals to mass over volume, Therefore, density of solution equals to mass of solution over volume of solution. To get your mass, you just have to move your volume here. Since we already have our volume 200 mils, it will times with your density lah. Okay, so then you can get your mass of solution and plug in your value. Okay, so from there you can get the heat change, Q reaction. Alright, so Q reaction will be negative something lah. Okay, but the question asks for heat released by the reaction. So that means this is actually negative Q reaction. So how do we get negative Q reaction? Basically, just make sure that this is, after you get your answer, then you just times the whole equation with negative. Okay, so yang ni contoh awak dapat negative X. Okay, daripada atas sini. Okay, this one jadi yang ni. Okay, so then you will get a positive value lah. You should get a positive value. So heat release by the reaction is 2.812 kilojoule. Alright, heat release. Okay, tak adalah negatif tu. Okay, please note that heat change is Q reaction. Okay, heat release is negative Q reaction. Enthalpy of reaction is delta H. Okay, so delta H is heat change over number of mole. Mole refer to whatever specific reaction that you have. Okay, kena tengok enthalpy punya definition. This is from 2.1. Very important. Okay, guys. Alright, this one you can do it by yourself. And then now we're going to look at bomb calorimeter. So bomb calorimeter or constant volume calorimeter is made up of a strong steel vessel. And you have water inside it. Sometimes it can be empty as well. Alright, this kind of calorimeter is used when you have combustion reaction, or other solid gas reactions. How do we use this bomb calorimeter? Basically, let's say if we have combustion reaction, combustion of a substance. So your substance will be put in this tightly sealed steel chamber. Our system is in here, so because of this steel chamber, it has constant volume. That's why we call it constant volume calorimeter for bomb calorimeter. Okay, so what will happen is that when we burn our substance in here in excess oxygen, alright, then your heat of reaction will be released. So it will be absorbed by water and calorimeter. Alright, so here we have a stirrer, just like coffee cup tapi dia motorized stirrer, and thermometer for you to record the change in temperature lah. Alright, so your system is basically in here lah. When you release the heat, it will be absorbed by water and calorimeter for bomb calorimeter. So just like just now, this is your system. Just that instead of solution, it is water, calorimeter and reaction. So same assumption we will be using. No heat enters nor leaves the system. Therefore, Q heat of your system is equal to 0. Therefore, we will rearrange the formula to get the heat change of our reaction. It will be negative Q water, Q cal. So the heat released by your reaction will be absorbed by water and calorimeter. So for water, we will use MC theta. Alright, so this will be mass of water, specific capacity of water, and delta T, temperature change. And this one, just like before, heat capacity of calorimeter and delta T. So this is important as well. Bila saya letak benda ni je, it is important lah. This is the calorimeter, bomb calorimeter punya formula. So this is the reaction at constant volume, okay? So remember this information. Constant volume calorimeter maksudnya bomb calorimeter. And you have to remember who will absorb the heat released by your reaction. It is water and calorimeter, okay? Alright, so for example 5, let's look at this example, okay? So 1.435 grams of naphthalene, this is your substance, mass of substance. Cetan H8 was burned in a constant volume, bomb calorimeter. So we know that this is bomb calorimeter. Okay, automatically we know which formula to use. Okay, who will absorb the heat release from your reaction? Okay, the temperature of water increases from T initial to T final. Alright, if the mass of water surrounding the calorimeter is this, so this is the mass of water, and the heat capacity of bomb calorimeter is this, so maksudnya this will be your C cal. Alright, capital C. Calculate the heat of combustion. Heat of combustion of naphthalene. So is this Q reaction or is this delta H? So if it says heat of combustion atau enthalpy of combustion, that means this is actually delta H combustion. Okay, bukannya Q reaction. But to find delta H, you need to know the Q reaction. Okay, heat change of your reaction. So first thing you need to know to do is to extract out your information. Okay, extract out your information. So once you have all the information, okay, all this, make sure to find delta T, your mass of water, your C cal. Alright, so I change this to joule per degree Celsius instead of just kilojoule. Okay, supaya senang saya nak buat calculation later, dia tally. And then you need to know the last formula that you need to use to find the heat of combustion. It will be heat change of reaction over the mole of your substance that is burned. Okay, so this one, again, it is important for you to know the definition of each of the enthalpy change. Okay, each of the enthalpy change punya reactions. Okay, so for combustion, 1 mole will refer to substance that is being burned. Okay, in this case it will be cetan H8. Alright, kalau awak tak tahu yang actually you need to divide by your substance that is being burned, then you might have divide it with, let's say, the mole of water from this mass. So maksudnya nanti jawapan awak salah lah. Okay, because awak ada salah part sini. So make sure to know, okay, 2.12 definitions too, very important. So next we know that it is a bomb calorimeter, so we need to know this formula. Okay, once you know that formula, everything else will be easy. You're going to just plug in your values. Okay, make sure it's in the correct units. Alright, and then we will get our heat change. Okay, so heat change for this combustion reaction is negative 57.61 kilojoule, meaning 57.61 kilojoule of heat has been released during the combustion of 1.435 grams of naphthalene. Okay, so make sure to understand what you are doing, because I will be asking during meet and okay. Alright, so next thing to do once we already know the heat released by the reaction is we want to find the heat of combustion, kan? So that will be your delta H. So since we already have the mass of our substance being burned, cetan H8, then we will just find our mole. Okay, so mass over molar mass, you will get mole. Okay, okay, since we already have this, okay, the heat change when 1.435 grams of cetan H8 was burnt, Okay, this amount of heat has been released. Therefore, to find the heat of combustion, you just need to put in your heat change during reaction and divide it by the mole of naphthalene that was being burned. Okay, so we have two methods to find your delta H, heat of combustion. Okay, you will need it to be in joule per mole atau kilojoule per mole. Okay, so the first way is you have to write down the chemical reaction for combustion. So for combustion is your substance will be burnt in excess oxygen, okay, to get carbon dioxide and water lah. Okay, so 1 mole in your definition of combustion, enthalpy of combustion will be referring to C10H8. So you're going to divide by that. So you can use this method, which is like stoichiometry, where you compare the number of mole with the heat loss, okay, heat released. Okay, so this one is basically the mole of C10H8 that was being burned. So since this amount of C10H8 releases 57.61 kilojoule of heat, then you want to find for 1 mole of C10H8, it will release this amount of heat. You just divide lah. Okay, this divide this, you will get 1. So you just divide this one with the same value. So this means that 5.14 times 10 to the power of 3 kilojoule of heat will be released when 1 mole of naphthalene is being burned. Okay. Method 2 is that we find the, I think this is easier. I like this better because it's more direct. Okay, we already find the heat change for combustion reaction and we find the number of mole of naphthalene that was being burned. Okay, and then we just divide our values together and then we will get the heat of combustion. Okay, when 0.01121 mole of naphthalene was being burnt. Alright, so make sure your answer for enthalpy of combustion or heat of combustion, remember those terms, will be negative 5.14 times 10 to the power of 3 kilojoule per mole. Right, so for heat of combustion or enthalpy of combustion, okay, or whatever reaction, your answer should be joule per mole or kilojoule per mole. Okay, for heat of reaction, Q tadi, Q, it will be in just joule or kilojoule. Okay, it doesn't have to specifically be for per mole. Kalau heat of atau enthalpy of whatever reaction, it must be in joule per mole or kilojoule per mole. Alright, okay, I think that is the last example that I will be explaining. So this exercise, do it yourself, and we are done with 2.2. Thank you.